Welcome back. Last time we took a deep dive into the capabilities of LaFA, especially how it enhances multimodal instruction following in large language models. It's fascinating because we saw how these models handle complex visual and textual information together, right?
Absolutely. It was a really insightful episode. And now, shifting gears to today's topic, we're tackling another key challenge for large models: efficiency. I think this paper on speculative decoding, or SpecDec, is a perfect follow-up. It looks at how to improve the speed of these massive models, which seems especially relevant for applications where response time really matters.
Exactly. SpecDec comes in with a technique that could potentially address the slower processing speeds we often encounter in large models, especially those used in real-time, interactive scenarios. Speculative decoding brings a new approach by allowing the model to process multiple tokens in parallel without changing the actual outputs. This is particularly important in systems that need quick, consistent responses. Think chatbots, translation services, or interactive assistants.
Right. And I remember from the paper, they mentioned that SpecDec manages to achieve all this speed improvement without retraining or modifying the model. That's a big deal because it makes the method adaptable to existing models, even the big ones like T5 or Lambda.
Exactly, it's one of the standout contributions here. By using a smaller, efficient approximation model to handle initial guesses, SpecDec allows the larger model to verify these guesses without slowing down, ensuring the same distribution as the original model. This makes it versatile and applicable across a range of tasks without extra overhead.
And that broader applicability is exciting. We're looking at something that could improve response times across different applications, from text summarization to machine translation. Plus, it sounds like it would fit right into models that we talked about, like LaVA, by making interactive tasks more responsive.
Yes, and that's where today's episode will take us into the details of how speculative decoding works, from its underlying principles to its applications and performance gains. We'll be breaking down each part, seeing how this speculative execution technique manages both speed and reliability, and discussing what this could mean for future models.
I'm ready to dig in. So, let's kick off with the setup and see how this technique really unfolds in action.
All right, let's dive into the abstract of this research paper titled Fast Inference from Transformers via Speculative Decoding. The core problem tackled here is that large transformer models, such as those used in language processing, can be slow to run. The authors have introduced a new method called speculative decoding to make these models work faster without changing the model's outputs. The key idea is to compute multiple tokens in parallel, which is a big shift from the traditional way of processing each token one at a time. Essentially, they're proposing a solution to speed up the decoding process of transformers, making them faster and more efficient.
So, speculative decoding is all about speeding up the processing time without changing the actual predictions of the model, right?
Exactly. One of the unique aspects of this method is that it accelerates the inference process, but ensures the outputs remain the same as if they were generated through the standard, slower approach. This new method works by combining a smaller, more efficient model with the larger model. The smaller model generates guesses or initial predictions that the larger model can then quickly verify and accept if they meet certain criteria. This way, several tokens can potentially be processed at once.
Why would we use a smaller model first? Is it because it's faster to process?
Good thinking. Yes, using a smaller model is indeed faster. The smaller model approximates the predictions of the larger one. By using these approximations, they can make initial guesses that might match the larger model's output. When the larger model verifies these guesses, it can accept multiple tokens in one go, if they align with its predictions. This parallel processing is what allows the speed up.
So, this method leverages two main points: using a smaller model to get initial guesses and then having the larger model confirm them in parallel. But is the approximation always accurate?
Great question. Not always. Sometimes the guesses from the smaller model may not align with what the larger model would predict, and in those cases, the larger model makes adjustments by rejecting certain guesses and recalculating. But overall, the method is designed to maximize the chances of alignment so that multiple tokens can still be processed together efficiently.
I see. It's like a quick filter with the smaller model. If the guesses don't match, they're reprocessed by the larger model, but this doesn't happen too often. What kind of speed up can they achieve with this method?
According to their experiments, they managed to achieve a 2 to 3 times speed improvement using speculative decoding on a model called T5XXL. This model is particularly large, so the efficiency gain is significant. They also emphasize that this acceleration doesn't require retraining the model or changing its architecture, which makes it easy to implement in existing systems.
That's impressive. It seems practical too, since they don't need to change or retrain the model. It's just about adding the speculative decoding approach on top of what they already have.
Precisely. This makes it suitable for production environments where reconfiguring or retraining models is time-consuming and costly. This paper's main contributions are the speculative sampling technique, which allows for this parallel processing, and the speculative decoding method, which utilizes it effectively for fast, accurate generation from transformers.
So, the speculative sampling part is about generating and testing guesses, and speculative decoding applies that to the model for speed. That sounds like a useful strategy for any setup needing real-time responses.
Exactly, you've got it. In summary, this abstract highlights how speculative decoding optimizes large transformer models' performance by accelerating the inference process. It does so in a practical, adaptable way, achieving faster results without compromising accuracy or requiring complex model changes. So building on what we've discussed, let's transition into the introduction, which sets up the broader context and motivation behind this study. The authors begin by highlighting the importance and power of large autoregressive models, like transformers, in tasks that require processing language data. However, these models come with a significant challenge. They're slow to decode, especially when we consider that each token generation happens in a serial, step-by-step fashion. So the problem lies in the fact that with every token, the process has to essentially restart for the next one. In other words, if a task requires generating, say, 50 tokens, the model has to go through 50 separate steps, one for each token. That kind of sequential process can become really time-consuming with larger models, right?
Yes, it sounds like the current setup creates a bottleneck because each token is generated one after another, and it's not really taking advantage of the potential for parallel processing.
Exactly, you've got it. This bottleneck becomes particularly obvious with models like GPT-3, LaMDA, Parti, and Palm, which are powerful but quite large. Even though they're capable of amazing things in natural language processing, image generation, and translation, their slow token-by-token decoding process limits their efficiency.
And because they're larger, each decoding step naturally takes more time. So, as the model's capacity increases, it also becomes slower, especially when each step needs to happen in order.
That's correct. And because of this, there's a pressing need for strategies that can speed up inference from these models. Now, some methods already exist to make inference faster. There are techniques aimed at reducing the overall computation cost for every input, like distillation, quantization, or even using sparser models. But these often require modifying the model's structure or retraining it entirely, which isn't always feasible.
Right. So while these methods can reduce computation, they often involve a lot of re-engineering, which might not be practical, especially in production environments where you want minimal changes to existing systems.
Yes, and that's where the authors see a gap and an opportunity. They argue that instead of altering the model itself, it's possible to focus on a different kind of efficiency, specifically concurrency. Their approach with speculative execution leverages this idea by allowing multiple tokens to be generated concurrently, which sidesteps the need for structural model changes or retraining while still addressing the speed issue.
So, speculative execution essentially adds parallelism without needing to touch the model's core setup. That sounds like a promising alternative to the usual approaches that require a lot of modifications.
Exactly, and it's built on an interesting observation, too. The authors note that in many cases, the bottleneck isn't from computation itself, but rather from memory bandwidth and communication delays. This leaves room to add concurrency, basically, making sure the model uses all available computation resources effectively.
So, rather than cutting down on computation, they're suggesting using available computation power more effectively by allowing parts of the task to run in parallel.
Precisely. And this led them to develop their speculative decoding approach, where a faster, smaller model helps generate initial guesses, and then the larger, target model verifies those guesses in parallel. This way, if the guesses are accurate, multiple tokens are processed at once, significantly reducing the time needed for each decoding step.
That approach sounds efficient, using the smaller model as a helper to make the larger model's job faster without altering the larger model itself. It feels like a balance between speed and model stability.
It's a smart balance, indeed. So, in summary, this introduction provides a thorough foundation for why accelerating transformer models is essential, and how the authors aim to achieve this by focusing on concurrency instead of architectural changes. They're setting the stage for the speculative decoding approach as a new and practical alternative to the existing speed-up methods. With that background, let's move into the core part of this method: speculative decoding. This section dives into how speculative decoding actually works to accelerate the inference process. The primary idea here is to use two models: a larger target model, which is accurate but slower, and a smaller approximation model, which is less accurate but much faster. To get started, the process begins with the smaller model, which generates a set of guesses or possible token sequences. These guesses then act as speculative inputs that the larger model can evaluate all at once. If the guesses align with what the larger model would have produced, they're accepted, and the process continues without having to redo computations for each token. Does that make sense so far?
Yes, so it's like the smaller model is making preliminary suggestions. And if those suggestions are accurate enough, the larger model can validate them in bulk rather than recalculating each one individually.
Exactly. By validating multiple tokens at once, this approach allows for substantial time savings, especially with larger models that are computationally intense. This technique leverages what they call speculative sampling, which is a method to ensure that, statistically, the accepted guesses reflect what the larger model would have generated without speculation.
I see. And this speculative sampling is what allows the method to still be accurate, right? Even though it's using a smaller model to generate these guesses.
Speculative sampling is carefully designed so that even though we're relying on the smaller model initially, the results remain consistent with the outputs of the larger model alone. To add another layer of robustness, when a guess from the smaller model is rejected, the larger model steps in to correct that particular token, ensuring accuracy isn't compromised.
So even if some tokens are rejected, the process still moves forward with accurate results, just with a slight adjustment to keep things aligned with the larger model's distribution.
Yes, that's correct. This setup of generating multiple tokens in parallel but verifying them with the larger model creates an efficient balance. It reduces the total number of steps needed for the larger model, since not every token has to go through a separate decoding step.
This must lead to a significant reduction in processing time, especially when multiple tokens can be validated together rather than one at a time.
That's the key benefit. According to the authors, this speculative decoding approach can yield a 2x to 3x improvement in speed, depending on the task and model setup. This makes it an attractive method for applications where both speed and accuracy are crucial.
And it sounds like it's quite practical too, since they're just adding this speculative layer on top rather than changing the actual model architecture or retraining it.
Precisely. The speculative decoding method is designed to be implemented with minimal disruption, which is why it's effective in scenarios where there's no time or resources to adjust the model structure. This method takes advantage of available computational power for parallel processing without altering the core model, making it a highly adaptable solution for speeding up transformer inference in real-time applications. All right, now that we've covered the speculative decoding approach, let's move into some detailed analysis in sections 3.1 through 3.3. These sections explore the technical underpinnings and quantify the method's effectiveness. First, in 3.1, the authors analyze the number of generated tokens, or more specifically, how many tokens the model can produce in a single speculative decoding run using this method. This gives us insight into the speed gains and how often the larger model actually needs to intervene. The analysis introduces the concept of the acceptance rate, represented by beta, which is essentially the probability that the larger model will accept tokens generated by the smaller approximation model without modification. This acceptance rate is crucial because the higher the beta, the more tokens we can process in parallel without needing corrections from the larger model.
So, if beta is high, it means the smaller model's predictions are more in sync with what the larger model would predict, allowing us to speed up by reducing the larger model's workload.
Exactly, that's the idea. When the acceptance rate is high, it indicates that the smaller model is doing a good job of predicting tokens that align with the larger model's outcomes, thereby allowing multiple tokens to pass through without needing recalculation. The authors use this acceptance rate to compute the expected number of tokens generated in each step of the algorithm. This relationship is expressed through a formula that factors in beta and the number of guesses, denoted by gamma.
I see. And I assume this formula helps quantify how many tokens we can generate per run and, consequently, estimate the potential speedup.
Right on target. The expected number of generated tokens depends on both beta and gamma, and understanding this gives us a concrete way to anticipate speed improvements. In simple terms, if beta is high and gamma is set well, speculative decoding can yield significant speed gains by reducing the number of times the larger model has to step in. Moving on to 3.2, this section discusses the calculation of alpha, which is the average acceptance rate across different prefixes. They calculate alpha by using a statistical divergence measure called DLK, which gauges the similarity between the output distributions of the larger model and the approximation model. Essentially, a lower divergence means that the smaller model's outputs are closely aligned with the larger model's outputs, leading to a higher alpha.
So, the idea is to quantify how well the approximation model mirrors the larger model by looking at the output distributions, right?
Yes, exactly. The closer these distributions are, the better the smaller model performs as a proxy, which means that speculative decoding will likely be more efficient. This analysis helps the researchers choose the right smaller model and refine its performance for different tasks. Finally, in 3.3, they delve into the wall time improvement or the practical speedup we gain by using speculative decoding. Wall time here refers to the actual elapsed time to run the model, so the authors use it to measure how much faster speculative decoding performs compared to traditional decoding. They derive a formula showing that the improvement factor is linked to both gamma and alpha, as well as a hardware-specific factor they denote as C, which represents the cost of running the smaller model.
So, this analysis connects all the pieces, from the number of tokens we can generate to the acceptance rate and even the impact of the hardware setup?
Exactly, it's a comprehensive look at how all these variables influence the method's efficiency. The formula gives a realistic projection of the speedup one can expect from using speculative decoding, making it a valuable metric for practical deployment. In summary, this section of analysis lays out how speculative decoding achieves its efficiency by leveraging the acceptance rate and wall time improvement formulas. This framework provides a clear understanding of the speed gains possible through this approach, reinforcing its practicality and scalability. Great, let's continue with the next part of the analysis, covering sections 3.4 to 3.6. Here, the authors dive into specifics on how speculative decoding impacts computational load, choosing the best parameters, and selecting approximation models. Let's start with section 3.4, where they explore the number of arithmetic operations. Essentially, this section calculates the computational cost of running speculative decoding compared to traditional methods. In speculative decoding, each time we sample guesses from the approximation model, MQ, we end up doing parallel runs with the target model, MP, as well. This means that the number of arithmetic operations increases proportionally with the number of guesses we make, denoted by gamma. However, the efficiency gained from accepting multiple tokens at once often offsets this extra computation.
So, even though we're doing more computations by running MP multiple times in parallel, the overall time savings from processing several tokens at once make it worthwhile?
Exactly. The extra arithmetic operations are considered an acceptable trade-off because of the parallel processing advantage. The authors even provide a formula to show the expected increase in the number of operations, factoring in variables like gamma and a ratio called C-hat, which measures the computational cost of the approximation model relative to the target model. Next, in section 3.5, the focus shifts to determining the optimal value of gamma, which is essentially the number of guesses we should generate in each step. This part of the analysis explores how to balance gamma based on factors like the acceptance rate, alpha, and the hardware setup. For instance, if alpha is high, fewer guesses might be needed, since the smaller model's guesses are more likely to align with the larger model's predictions.
That makes sense. So, if the smaller model aligns well with the larger model, we don't need as many guesses, which would save computation time. But if alpha is lower, we'd want more guesses to make sure we capture the right output.
Precisely. The authors provide a formula to calculate the optimal gamma, showing that this balance between alpha and gamma can yield the best speed improvement. They also discuss how hardware configurations impact this choice, emphasizing that gamma should be optimized based on the specific computational resources available. So the optimal gamma isn't just about model alignment, it's also tied to the capacity of the processing setup.
Got it. So, finding the right gamma value is about efficiency on both the model side and the hardware side. And I assume this would vary depending on the specific hardware, right?
Yes, that's correct. Different setups might benefit from different gamma values, and optimizing this can significantly impact the performance gains from speculative decoding. Lastly, Section 3.6 discusses choosing the approximation model, MQ. The authors emphasize that MQ should be small enough to be fast but still effective at approximating the larger model's outputs. In their experiments, they find that smaller transformers work well as approximation models, often choosing ones that are around 2 orders of magnitude smaller than MP.
So they're balancing model size with alignment accuracy. A smaller MQ would be faster, but it might not align as closely with MP, which could lower alpha. But a larger MQ might align better but slow down the process.
Exactly, and that's the balance they aim for. The authors even experiment with different types of approximation models, including trivial ones like n-grams, which provide surprisingly decent speed improvements in certain cases. For instance, even a simple bicaram model yielded a reasonable alpha and speed-up for certain tasks. Overall, this part of the analysis highlights that by carefully selecting an approximation model, optimizing gamma, and managing the computational load, speculative decoding can maximize both speed and accuracy without fundamentally altering the main model. This adaptability is a significant advantage for real-world applications. Now that we've looked at the theoretical setup, let's see how these concepts perform in practical tests, as detailed in the experiments section. Here, the researchers conducted tests to measure the real-world speed gains from using speculative decoding with various approximation models, focusing on tasks like English-German translation and text summarization using the T5XXL model. The setup involved testing the T5XXL model for both translation and summarization tasks, using 3 different configurations of smaller models, T5 small, T5 base, and T5 large, as the approximation model MQ. They measured the wall time, or actual elapsed time, with a batch size of 1 on a single TPUV4 for different sampling methods, like argmax and standard sampling.
So, they're testing how each smaller model, or MQ, compares in terms of speed improvement and alignment with the target model T5XXL. And I assume the results vary depending on the sampling method used, right?
Absolutely, that's a good observation. For example, with argmax sampling, which chooses the most probable tokens directly, the speed improvements were quite notable, up to 3.4 times faster for translation using T5 small. With standard sampling, which introduces more randomness, the gains were slightly lower but still significant, around 2.6 times faster.
That's impressive. It seems like the choice of MQ and the sampling method both play a big role in determining the speed gains. So, T5 small was the most effective approximation model?
Yes, exactly. The T5 small model struck the best balance between speed and alignment with the larger T5XXL model, particularly for the argmax sampling setting. The results show a trade-off. While larger approximation models like T5 large are closer in output to the target model, they also add to the computational load and reduce the speed gains somewhat. Another interesting result from these experiments was the alpha values observed. Recall that alpha represents the likelihood of the larger model accepting tokens generated by the approximation model. Across various configurations, they observed that alpha increased with the size of the approximation model, as expected. This means that a larger MQ generally provides higher acceptance rates, though it's a trade-off against processing speed.
I see. So there's a direct relationship between model size and accuracy in this case. Larger models give better accuracy but come at the cost of some speed, while smaller models like T5 Small still manage to give decent accuracy with much faster processing.
Exactly. So in summary, these experiments highlight the practical viability of speculative decoding across different tasks, showing that with the right approximation model and sampling configuration, it's possible to achieve substantial speed improvements without retraining or modifying the core target model. Now let's transition into the related work section, where the authors discuss previous research that has aimed to speed up inference for large models. Here, they explore how other researchers have tackled the challenges of improving inference efficiency in transformer models. The primary approaches mentioned include techniques like distillation, quantization, and sparsification, all of which reduce computation but generally require altering the model architecture or training process. One of the common methods is model distillation, where a smaller model learns to mimic a larger one's outputs, achieving faster inference times. This approach is effective, but does mean training a new, smaller model specifically designed for speed.
So with distillation, they end up with a different, smaller model that doesn't necessarily have the same architecture but can approximate the larger model's behavior.
Exactly, that's the trade-off. While distillation produces faster models, the outputs may not be identical to the original models, especially under different input conditions. Quantization and sparsification, on the other hand, reduce the precision or density of computations within the model, which can accelerate inference without a complete retraining. However, these changes can impact the model's performance if not implemented carefully.
So, while quantization and sparsification provide speed, they need fine-tuning to ensure the model remains accurate enough for its intended tasks?
Correct. It's a balancing act between speed and maintaining the model's effectiveness. Additionally, there are adaptive computation approaches, where the amount of computation varies depending on the complexity of each task or input. For instance, some methods use early exit techniques, allowing simpler inputs to require less computation and thereby speeding up the process. They also mention work related to parallel decoding techniques, such as blockwise parallel decoding, which decodes multiple tokens simultaneously. However, unlike speculative decoding, this method is often limited to deterministic or greedy decoding methods and doesn't fully support probabilistic or stochastic decoding scenarios, where some randomness in output generation is involved.
It seems like speculative decoding offers an advantage here by maintaining the flexibility of stochastic decoding while still achieving parallelism.
Exactly. Speculative decoding is unique in that it doesn't require changes to the core model, training process, or architecture, unlike many previous methods. Instead, it adds a parallel speculative process on top, which is what allows it to maintain the original output distribution while speeding up the inference. This approach essentially opens up new avenues for improving transformer inference without the downsides of model alterations. So the related work section underscores how speculative decoding fits within and builds upon prior research, providing a fresh approach to balancing speed, accuracy, and adaptability in large transformer models. All right, moving into the discussion section, the authors reflect on the strengths and limitations of speculative decoding. First, they highlight how this method provides significant speed improvements, up to 2x to 3x faster in some setups, without the need for model retraining or architectural changes. This flexibility makes it particularly attractive for practical applications where models are already in production and can't be easily modified. One key point they address is that the method achieves this speed by increasing concurrency, but it does come at the cost of more arithmetic operations. So, while speculative decoding saves time, it's only suitable for environments where extra computational resources are available to handle this added load.
So, if a setup is already limited in computational resources, speculative decoding might not be the best option. It sounds like there's a trade-off between time and computational power here.
Exactly, that's the trade-off. The authors suggest that speculative decoding works well in cases where the bottleneck isn't arithmetic but memory bandwidth, as in many large-scale models. In these scenarios, the added arithmetic operations don't cause much overhead, and the speed-up becomes highly beneficial. They also touch on future research directions, For instance, they mention exploring the compatibility of speculative decoding with beam search, which is commonly used for tasks requiring high-quality, diverse outputs. They're curious whether speculative decoding can be adapted to this more complex decoding method.
Interesting. And since beam search is widely used in machine translation and summarization, making speculative decoding compatible with it could expand the method's usefulness.
Absolutely. Beyond that, they propose ideas like creating custom approximation models or even implementing a hierarchical setup where a faster model could speed up the approximation model itself. This could open doors to even greater efficiency gains. In summary, this discussion reflects on speculative decoding's current impact and future potential, emphasizing its practical value and adaptability across various configurations and possible improvements. All right, that wraps up our deep dive into speculative decoding. We've covered everything from how it uses an approximation model to boost processing speed without retraining, to the impressive applications it unlocks across large-scale language tasks.
Yeah, and it's pretty amazing to think about the flexibility of this approach. I mean, SpecDec can enhance performance without needing a ton of new resources or architectural changes, which makes it adaptable to almost any existing model.
Absolutely. And beyond the theoretical gains, this technique has practical implications for real-world applications, especially in tasks requiring quick response times like live translation or real-time AI interactions. There's so much potential here for future models, especially in optimizing both speed and reliability.
I agree. It'll be interesting to see how methods like SpecDec evolve and get integrated into other fields or even in multimodal applications we talked about in previous episodes.
Definitely something to watch for. And thanks to everyone listening. We hope you enjoyed exploring how speculative decoding is shaping the next wave of model efficiency.
Yes, thanks for tuning in. Can't wait to dive into more exciting topics next time.